Great, thank you very much. Yeah, so yeah, since this is the last, I think this is the last talk of this series. So I really like to thank the organizers. Yeah, for putting this together. It's been really fun. Yeah, so I thought for the last talk, my goal is just to show you some pictures, and yeah, hopefully get your interest in some open problems. Okay. So here are some recaps from lectures 1 and 2. At least for this series, tropical geometry really just mean take the convex transform of a piecewise linear convex function. And then once we've done so, then we have, say, basically a set of points, some point configuration. We take the convex hull and we look at the regular subdivisions. And that turns out it contains a lot of interesting combinatorial information on the original object where this tropical geometry came from, right? So using that strategy, last time we turned questions on auctions into questions about discrete convex geometry upon which we could give solutions. Okay. So today I'll just give you some more examples. The first one is polytopes and algorithms and semigroups. Yeah, so I hope this will be an interactive lecture. Okay. So here's a definition. The bicyclic monoid is the free group on two letters with the relation that BA equals 1. Okay, so note that AB does not equal 1. Right? But yeah, just BA. So a word is a string of letters. For example, let's string together some letters. An identity UV is a word pair such that U equals V. And if you replace A for B and B for A in U, and you do the same thing in V, then you also get an equality. So here's an example or small question. Is this word ABBA, does it form an identity with the word AB? Please just yell out your answer, or you can type it in the chat. Okay, so let's check. Oops, sorry, for some reason this thing is not. Okay. Let's check, right? Oops. And more. Yes. Okay. Lots of people think yes, so let's check. So the answer is actually no. So why is that, right? Because if I do ABBA, well, BA is just the identity, so that indeed is equals to AB, so I'm good. But now if I swap A for B and B for A in here, then I get BA AB, okay? BAAB is the same as AB, right? But when I apply the same operation on this guy, then I get BA, which has become the identity, right? So on the left, I have AB, which is not the identity. And on the right, I have 1. And so when I do this swap, I don't have an equality, right? So in this case, this word is not equivalent to the other word, okay? All right, so is the trick clear? By the second property. Yes, thank you. That's right. So the first property is satisfied. I totally agree. And then indeed, the second property is not satisfied, as we just briefly look at. If we swap AB and BA on both sides, then you don't get the same thing. So so there's always a trivial identity, which is 1 is equivalent to 1. Okay, there's no A and B's to swap, so that's fine. Here's a question for you. Can you construct a non-trivial identity? So can you construct a string of words, well, a string of letters, right? Such that first of all, if you cancel all the BAs that stand next to each other, then you get an equality. And secondly, if you swap A and B around, then you still have that property. So I'll give you, say, a minute. Okay, let's try is A, B, A, is that okay? So definitely this is okay. And now if I do sigma of this become B, A, B, and that's the same as B. Yep, so that's definitely good. Here's another one, B, A, B, A is the same as B, A, right? So yeah, I think that one's also good, right? Because that's they both fine, right? They both equal to 1. And if I apply sigma on both sides, then this becomes AB, sigma on the other sides become AB. This guy cancels, you got AB. Awesome. Okay, great, thank you. All right. So, right. So these identities, as you notice, here are some examples, right? Thank you very much. So as you notice, these identities have different lengths on either side. Okay. So I guess I must apologize because I cheated a little when I defined this. Right. So so the more interesting case is when let's add another constraint here, which is that the length of U has to be equal to the length of B. Okay, to look at non-trivial ones. Yes, so I agree with you. If you didn't have this length constraint, then there are actually quite a lot of very short identities. Okay. Right. Okay. But if we have the length constraints, then it's actually not so easy to construct at all. Okay. So how long? Wow. Okay. So yeah, how long do you think is the shortest non-trivial identity with the constraint that the length of the two words have to be the same? You can just guess the number. I think it's not so obvious to come up with one because the length constraint really put it stops you from like short circuiting just by inserting BA in the middle. Yeah. So just and any number that a random guess would be totally fine. 47. Thank you. Yeah, that's a good number, right? Okay. So it turns out here's an identity. This is an identity of length 10. Okay. So it's ABBA, AB, ABBA. This turns out to be equivalent to ABBA, BA, ABBA. Okay, so we can do a manual check, right? They both have length 10. This is the shortest identity known. So it's in a paper. I think originally the paper came out before 66. The 66 version is just the translation from Russian to English. Okay, great. So this is, my co-author Marianne explained to me. This is the Abappa identity. It's called put Abappa on the train to commute. You put Abappa on the train, and then the middle part will commute. Okay. So very nice way to remember it. So in general, there's some very interesting question coming out from semigroup theory, where people look at the bicyclic monoid and the morphisms. For example, how to construct an identity here, where a fixed length. Right? It's not so obvious at all. So we know the length has to be at least 10. But how do you construct, like, say, a family of, is there an identity for for an arbitrary length, right? And then if you could have a formula to construct them, could you say count them all, right? If I fix a length L, how many identities do I have on this length? If I fix, say, a word, if you give me a word, can I look at the set of all word V that is equivalent to this one, right? All the words V that form my identity with U. This is some set of words. Does it have any structures? Are there, say, generalizations of this free group with some non-commutative identity? And probably for me, the most interesting question is, this sounds fine, but where's the geometry in it? Okay. And if you're not convinced that, like, working with A, B, B, A, etc., it's your sense of fun. Well, here's a quote from many people in semigroup theory. The bicyclic monoid plays a very important role in the structure theory of semigroups. Okay. Okay, so that's, I would be honest with you, that's basically as far as I know about semigroup theory. I did try, honestly, to know a bit better, but it's beyond my abilities. Okay, so to me, the interesting part come into the tropical connections, which again allow us to get some polytopes out. Okay, so here's a theorem that's not obvious at all, which is, let's consider the ring of max plus tropical polynomials in 6 variables. So I have 3 variables x, y, z for A, and I have 3 variables x, y, z for B, and I will identify the letter A with this matrix here. So this is an upper triangular matrix. It's 2 by 2, and the variables, the entries are the variables x, y, and z. Okay. Similarly for B, I have a 2 by 2 upper triangular. I think of it as a tropical matrix with variables x, b, y, b, z, b. Right. So now when I form a word, I'm just multiplying the corresponding collection of matrices together. Right. So if I have A, B, let's say A, B, A, then I'm tropically multiplying these 3 matrices, and I should get a new matrix, which I will call it the matrix of the word. It should still be upper triangular, right? Because this is the 0 identity. This is the additive identity in max plus, right? Since max of, if I have a number x, right, max with negative infinity, I always get that x back. So this is my tropical additive identity, right? So if I multiply a bunch of upper triangular matrices in tropical land, I still get an upper triangular matrix, but the entries over here are now polynomials, right? So now I have polynomials. These guys are polynomials, tropical polynomials in 6 variables. Okay, so here's a theorem, which is your word U. So U comes with now a matrix of involving 3 tropical polynomials. V now comes with another matrix involving, another 3 tropical polynomials. And the theorems that U and V are equivalent with the same length on the bicyclic monoid, even only if every single pair of polynomials here in MU and MV, they are equal as functions. Okay, so MU has something, something, something with negative infinity here, and I want that to be equals to MV, which is something, something, something. And I want to stress that I want to think of the equality not as algebraic equality, so I don't need the same multiplicity for every monomial, but I need that they're equal as piecewise linear convex functions. Okay. Right. So this theorem came out, I think, not too long ago. About the archive version was about 5 years ago. It's not easy to see, but for us is an excellent tool to get to tropical geometry and polytopes. Right. So just a quick reminder that in tropical land, you can have, you can have two functions that are equal as functions, but they don't have the same algebraic expression, right? So here's an example. If I do a binomial expansion in tropical land of x plus 3 to the power of 2, I could get one expression on this side. But because max is idempotent, right, this is literally max of 2 times x, x plus 3, and 2 times 3. If we plot this function, we would find that this middle terms never achieve the max alone. So you could actually, for the same, to express the same function, you don't need them. And so therefore, you can simplify to create a new algebraic expression, right? So f and g, they're not equal algebraically, but they are equal as functions. Right, in the sense that if I stick in any x on either side of the expressions, I get the same number back. Okay, so this is something unique to the tropical algebra. This is not true over, say, complex or real. Okay. So, right, so we saw all the way back from lecture 1, when the two tropical polynomials equal as functions, right? If I have polynomial f and g, right? Think of them as functions just mean I think of them as piecewise linear convex things, right? And so they're equal as function if and only if their convex transform are equal. And the convex transform, because they're piecewise linear, the convex transform is just the lower convex hull of a bunch of points, right? The graph of the convex transform. Okay, so I just need the convex hull of a bunch of discrete points to be equal, right? So that's, so again, I have f, it finds like a lift, right, of some set of points in ZD, right? And I have g, and it defines like another lift, right? So one lift could have many, many more points than others, right? These AF and AGs don't have to be equal. What I care about is when I take the convex hull, right, then I should have the same function, right? I have the same number of vertices and same, all the piecewise linear pieces are the same. Okay. And for us, it's even better because our polynomials have trivial coefficients. Okay, so all of the CI's here for us are just 0, right? Because when we multiply these matrices together, right? Let's say I multiply with xb, yb, zb here, right? If we look at this part, say, then that just become xa, xb, right? I don't pick up any xa tropical times xb. I started with, trivial coefficients, and so when I multiply a bunch of guys with trivial coefficients, I just end up with something with trivial coefficients, right? So that means my lift now is just nothing, just lift all the points to the height 0. So literally, it's just a question of I have a bunch of polytopes and I want them to be equal to each other. Okay. Okay. There's just a very small technical issue, which is, in the formulation I gave you, then I have, when I multiply, right, if I have a matrix, a word U, right, I multiply it out, then I get a matrix M, and it has 3 non-negative infinity entries. So that means I have 3 polynomials, and I need it to be equal to another 3 polynomials from V. So that's 3 pairs of polynomials, and they are polynomials in 6 variables because originally I started with 3 variables for A and then another 3 different variables for B, right? So I have 3 pairs of polytopes in dimension 6. Okay? That's kind of annoying to work with, and it turns out that there's a certain there's a certain algebraic structure in tropical matrix multiplication that one could exploit, and so that allows us to transform these polynomials to different pairs to reduce the dimension. Okay. So what it comes down to is a very, very cute graphical characterization of when 2 words are equal. Okay. So a word now, let's say take this one. I think of it as a upright path. Okay, where let's say whenever an A appear, we're going to make a right step that is you know, the path will step to 1, 0 to the right of where we are. And whenever B appears, then we'll take an up step, right? We'll increase the second coordinate by 1, right? So for example, this guy here, AB, BA, 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 B, this is, you know, this is A, B, B, A, B, A, B, A, B, right? This is a, well, that's the path corresponds to my word W. Okay. Now from here, from this path, I will form 2 polytopes, okay? And these polytopes will contain all information I want to know about whether this word W forms an identity with somebody else or not, okay? So we call this the signature of this word. So it contains 2 polytopes, and they're actually pretty easy to construct. So for the first one, we have this staircase, right? And we now imagine it as like a histogram of a function that goes from x to y, right? So this is x space, this is y space, and I imagine I want to turn this into a function, so I look at the picture from here, right? And for each value, I just take the highest, for each x coordinate, I just take the highest y value on the stair possible, right? So I have, as a result, I end up with these red points, and I would just ignore the last. I will ignore the last point here. This is the technicality thing. Okay. So now with that, I take the convex hull of the set of points, and that's my first polytope PW. Okay. And I could play the same game, right? Because of the kind of symmetry of this staircase path. I could now think of looking at this staircase graph and think of it as a function instead from y to x, right? So now I'm standing over here and I look onto this side, and my goal is for each y value, I take the highest possible x value on the staircase that corresponds to this y. Right. Okay, so I should get all of these points. And again, I ignore the value y equals to the last point. So here I also ignore the value x equals to the last one. I don't take a point there. Same thing down here. I just ignore that last value. Right? So in this case, I end up with these 5 points. I take the convex hull, and that's my second polytope. Right? So now I have 2 polytopes. They're nice, and you know there's a certain symmetry in this path, right? In that if I reverse the path, right, then it's effectively correspond to, you know, swapping the pair P and Q. And here's the main theorem, is that if you have 2 words, that gives you 2 different paths, right? Each path gives you 2 pairs of polytopes. Then these 2 words form an identity if and only if their signatures are equal, right? So that is the P polytope of W has to be equals to the P polytope of V, and the Q polytope of W has to be equal to the Q polytope of V. Okay. All right. So they're equal as polytopes in the sense that they equal. If I take the convex hull of the points, then they're equal. Okay. And the reason came from like the tropical geometry part. Okay. So here's a challenge. Let's look at this path here. Can you just modify this path slightly so that you end up with another word that has the same signature? Let me make this a bit bigger. Or maybe this is already as big as possible. I hope the question's clear, right? So I have, yeah. I basically now need to fix this P, well, fix this blue polytope and fix this red polytope. And the question is there another staircase path such that if I played the same game as before, right, looking in from below and look at the highest points possible and then from the polytope, then I don't, for the new path, I don't change this blue outline, right? Same thing, right? I need to slightly modify this staircase such that now if I were to look from this side, and from the Q polytope, then after modification of the staircase, this Q polytope is unchanged. Wait, I have to say. Flip the corners of the path marked in red. Thank you. Is it no equality? It's not up to any transformations. It's you have to be equal exactly. Yes, that's right. So thank you. You just flip this point here to here. So now I have this path. Okay, and let's analyze the effect of this gray path. Right. Right. So the effect of this on the P polytope is that now instead, at when x equals 2, the highest point on the staircase is this, right? When x equals 3, the highest point on the staircase is still this point, right? So my new, let's call this flip guy V, right? So now my PV is a convex hull of these red points, right? But the convex hull of that is still the convex hull of the original bunch of points, because this guy wasn't a vertex, right? And now he still is not a vertex. Similar here, the effect of switching this corner is now at coordinate 2, y equals 2, I have this point instead of this red point. But at coordinate 3, I still have this point, right? So my Q polytope is still is now the convex hull of these red points. And it's still the same as the convex hull of, the original set of points, where this red point was this guy before. Okay. All right. So that immediately tells us that, this word is equivalent to another word where what we, the result of this flip is that we just swap AB with BA over here. Okay. And it's a non-trivial identity because they have the same length. Okay. All right. So pretty much you can get from one word to another in an equivalence class by local flips like this. And this is like this implies that there's a certain structure to the equivalence identities of this is the bicyclic monoid. It's just it has a funny notation in our paper. Okay. Right. So here's just a short theorem, right? It said that this notion of equivalence, if I think of it as a notion of equivalence on path, right? So W is equivalent to V if and only if, I identify W with its path, right? Then this equivalent notion it respects the lattice structure of the staircase path, right? Namely, if I have a path W and a path V, right, here's W, here is say a path V where W lies, below V, the graph, the path of W lies below the graph of V, and suppose that V and W are equivalent, right? Then that means any path that gets sandwiched in between would also form a word that's equivalent to both V and W, right? Okay. And the reason is you can just if the upper guy, if the polytope of the upper guy is equivalent to the polytope of the lower guy, then you can show that you can recursively kind of push the corners in V down to transform the path V to the path W, and every time you do one of these local transformations, the polytope is unchanged, right? So that's effectively forms the proof. You can get all the local moves from B going down to W, right? And so as a result, if now I have a path W's and V that are equivalent, right? They might not, they have to be staircase paths, but they might not, one might not be bigger than the other, right? So I know that they belong to the same equivalence class. Then well, then I know in this class, I can just take the path that is lower bounded by them both, right? And I can take the, the upper path that, is bigger than them both, right? This is the, this path upstairs is the max path from B and W, right? And this path downstairs is the min path of V and W, right? Because V and W are equivalent to each other, then I know when I do this min and max a operation, then I still stay in the same equivalence class, right? So each equivalence class essentially is just a lattice, right? With where the a lattice with respect to the usual ordering of pairwise, ordering of piecewise linear, ordering of upright paths. I'm sorry, it's too early for me. Right? So every equivalence class now is a lattice with a smallest and a biggest element, right? So here are some examples, right? If I had that example before, then it turns out there's no more wiggle room in this equivalence class, right? I have this path. There's exactly one operation I could do, which is push this corner down to form this new path here. So as a result, this lattice is just pretty simple. It got a W and a V. Okay. I could get more complicated lattices, right? This one, for example, is isomorphic to a cube, 0, 1 to the 5, right? So the black path is the lower one, right? And that's the minimal element in my lattice. The red path is the upper one. That's the maximal element in my lattice. And I can get, to everybody in between by choosing which of these corners I want to push in, right? So there are 5 corners I can push down to form yet another word in the equivalence class. Okay. So, right. So first of all, I should remark that like this pair of polytopes is very interesting. Like I've never seen this done on a staircase path before. Staircase path has definitely been studied a lot in combinatorics, but the idea of forming, think of them as a pair. Think of them as functions. Think of the staircase path as some sort of functions. And take the convex hull of the set of points that has not been done before, right? So that's very interesting. It's a new object, and we can play this game beyond the bicyclic monoid. We can have semigroups of n by n tropical matrices on m symbols, right? So that is, I have symbols, let's say A, B, C. To each guy, I associate an n by n upper triangular tropical matrix, right? Okay, and again, right, I could say 2 words from an identity if and only if, right, the product of the corresponding matrices, they form, 2 big matrix that have that element-wise, the polynomials are equal as functions. Okay, so this family of tropical semigroup matrices, they're interesting in themselves, right? They of course they form a particular bunch of semigroups but if you choose particular parameters, then you recover sort of semigroups that people really like in semigroup theory, right? So when n is 2 and m is 2, then you get the bicyclic monoid. When n is 3 and m is 2, m is the number of letters, right? N is the size of the matrix. When n is 3 and m is 2, you get something called the Placktic monoid of rank 3, right? And these things basically there has been no good tools to study this before, but now, because we know it's just the same as these tropical matrices, and with these matrices, we have pairs of polytopes, we can hopefully solve problems on these well-studied semigroups, right, and make progress. Yeah, so our paper has a characterization that talk about, for arbitrary n and m, what are these pairs, what are these sequences of polytopes that you get. So when you increase n, that's when you get polytopes of higher dimensions. It's much more interesting, and there's still a lot of things we don't know about it. Right? But we already used it to, as a proof of concept, we just used it to answer some existing questions in semigroup theory. For example, there was Isaacian's conjecture that said that for the Placktic monoid of rank 3, so this is the case, n equals 3, m equals 2. The shortest identity of it is of length 26. Okay. Okay, so we just numerically, enumerate a bunch of identities. Right? So one thing here is that if something is an identity in this Pactic monoid rank 3, then it must also be an identity in the bicyclic monoid, right, that we saw before. Right? And so what we did then is we just numerically enumerated all possible identities for the bicyclic monoid of length up to, just keep going until the first time that we find an identity that also belongs to the Pactic monoid. Right? We had a way to check that that's the case. Okay. So just by exhaustive enumeration, we found that the length is not, shortest length is not 26, it's actually 22. And here's a bunch of these. Here is a bunch of these identities. So yeah, so manually checking this would be really terrible. I guess the way that we wrote it, you can see there is the beginning and the end part of the words are the same. So that tells you that the two paths are coupled all the way until there's a single swap, right? So basically the path looks like the paths are all the same up until there's exactly one box where in one guy it's the upper corner and in another guy it's the lower corner, and then beyond that they're all coupled again, right? So it's a very, very small modification. Right? All of these have the same picture. Right? So here's another one that I thought was very interesting, is that you can now do a probabilistic construction of identities. So before this, it was hard to construct identities, right? There were papers that the whole point of the paper is to construct very specific families that of infinite length, that has some interesting good of symmetry to them. It turns out if you just want to construct identities, we did numerical experiments and found it's okay just to take a very, very long random word. Okay, so if I take a random staircase path just by flipping coins, right? Make sure it's really long. Then there's a really high chance that that thing will form an identity with, something else, right? So once I fix the path, it's relatively easy to check, does it form an identity with anything else, right? Because that check takes, it's linear in the length, because all I need to check is I check all the corners and I just manually push these corners one way or the other. And I just check whether, the new words that are formed, whether that has the same polytopes as the one I ended up with, or the one I started with, right? So that's, quite easy to check. And we don't have a proof for this, but at least I think it would be nice to have a proof. But at least when we did numerically, then this is, your chance of failure. I guess it's a bit hard to see. This is 1. This is about 10%. The length here goes from 30 to 80, right? So by the time you get to paths of length 80, right? So path of length 80, I think specifically I'm looking at equals number of A and B. So my path of length 80 are paths in staircase path in a square 40 by 40, right? So by the time I get to a random staircase path in 40 by 40, my chance of failure in finding an identity with this probabilistic construction is about 15%. Right? So it's still non-trivial, but we guess that eventually this probability would go to 0. Well, it's very close to 0, can get arbitrarily close to 0 as L gets infinity, but there's no way to numerically verify that beyond that. Okay. So yeah, if there's a solution to this, that'd be great. And I think it has very interesting connections with random walks and Brownian motions. So there's still lots of open questions in this field. So here's an XKCD that said, our field has been struggling with this for years. Struggle no more. I'm here to solve it algorithms. And then crunch away 6 months later, oh, this is really hard. We've made a little bit of progress since, right? But then the questions that are left I think they fall in really interesting intersection between semigroup, polytopes, and then definitely because of staircase path and whatnot. If you take probabilistic view, then there's also kind of Brownian bridges, like somewhere in between. I think there some work to be done, and they're very interesting. Okay. So I just want to mention one thing about polytopes in higher dimensions that we get. This is if you work with n equals 2, then you just always end up with these. If you fix n equals 2 and make the letters bigger, then you just end up with staircase path in higher dimensions, but the signature construction stays the same, right? Which is now, for example, if I have 3 letters and here's my word, I think of it as this staircase path, right? Going from, let's say this is coordinate A, this is coordinate B, this is coordinate C, going from, the origin, all the way up until the top corner. The top corner should be however many A's that this word had, however many B that this word had, and however many C that this guy has. Okay. So from my path, I can now think of this path as sort of like a function, right? In 3 ways, right? And so therefore I get 3 polytopes as my signature, right? I could think about it as I'm keeping track of A, right? So therefore I look at I look at, this is A equals 0, this is A equals 1, and I look at the furthest, there's a proper definition for this, but for the picture, it's just basically I look at the furthest kind of, probably the easiest way to think now is to say for every node in this path, I can associate it to either A or B or C, right? And then, so before I draw some things on top, right? So for every node on this path, there's a consistent way to define it so that it can be assigned to exactly one of the 3 letters. And then the signature just consists of now 3 polytopes. One come from taking the convex hull of all the points that makes up A, that get assigned to A, right? So this is the PA. Well, let's call this PA. This is the polytope consists of, taking the convex hull of all the points that be assigned to B. And this is the polytope consists of taking all the convex hull of the points assigned to C. Right? So this assignment can be written down, and it's the same for dimension 2. It's the same as looking at the graph in 2 different ways. Right? Okay, so now I have 3 polytopes, and then again, the theorem is that W is going to be equivalent with V if and only if, right? W and V are 2 staircase paths such that their polytopes, their corresponding, polytopes, you have 3 pairs. Those 3 pairs are all equal to each other. So in this example, I believe, well, this is a triangle, so there's no room to wiggle, right? So is that one, and so is that one. So there's no, this guy does not form an identity to anybody but itself. Right? So this is all points are vertices, so they're not movable. So we call a guy that sits in its own equivalence class is called an isotherm. Right? So this is what happens when you fix n. If n is larger, say 3, right? Then you get a longer sequence of signatures, right? Which is you get more polytopes. There's more to check before you can declare 2 words are equivalent, right? So in particular, these 3 polytopes still stay. Those are the first 3 in your coordinates, and then you get I think either 3. Yeah, you get 3 more, right? They come from pairs, right? So you get 3 choose 2, many more, and there is an explicit construction that tells you how to say smash these 2 polytopes together to form another polytope over here, right? So you get a PAB, you get a PAC, and you get a PBC, right? Okay. So all the later polytopes, they are derived as some sort of projection of the sorry, I can't quite remember if it's the Minkowski sum or the product of these guys, but there's a certain, it can purely understood in terms of discrete geometry, okay? So there's a certain operations that will take these polytopes and produce new polytopes, and then, so that lengthen your signature, and then 2 words for a larger n, 2 words are equivalent if and only if their entire signatures are equal to each other. The entire sequence of polytopes are equal to each other element-wise. And I should say, we know what happens. We know how to form this bigger polytopes, right, when n is 3, but we don't really understand them, right? So I think it's not too difficult to understand them, but somehow we have sort of really struggled to kind of, for example, figure out what properties the staircase path has to take so that I get 2 equivalent sequence of signatures, right? 2 equal sequence of signatures. The main difficulty here is I don't have this kind of sandwich theorem when n is large, right? So here's an example where W is the red path, V is the black path, and unfortunately, so they are, and you know, they're polytopes. There's the blue. This is the blue polytope is the, if I just think of this as the case n equals 2, then I have you know, P is one polytope and then Q is the other polytope in green, right? And it's very clear that if I change these 2 points, if I flip these 2 points, then I don't change the polytope at all. So indeed, I have W is equivalent to V when I'm looking at the case n equals 2, right? But we numerically verified that if you look at the higher order polytopes, then these points, they define vertices of this higher order polytope, so that I don't have W is equivalent to V when I'm looking at bigger matrices, right? Okay. And so that tells us that the structural theorem where you can just push corners and still stay within the equivalent class, that holds for n equals 2, but that fails for n equals 3. And this has been like a major issue in working with this higher polytopes. We don't really know what operations on the words would actually preserve these higher ones. Yeah. Okay. Yeah. So one feature of our papers, we generated a lot of data. So the structure theorem is not the only thing. So for example, here we can check words with really, really big word length. So I sample, for example, the word length is 1,000. So this means I have 500 A's and 500 B's. I just generate a random sequence with 500 A's, 500 B's. And then I check all of its UT2, all of this equivalent class for n equals 2. And then I manually verify what's the fraction of these identities. Sorry, can you hear me? Yeah, okay. So then I manually verify what's the fraction of these identities that also form identities for n equals 3. Okay, so generally identities in n equals 2 like form a superset of identities in n equals 3, and this structure holds, right, blah blah blah, for n equals 4 and so on. So we get like a sequence, like a power of identity, right? But here I could just check if I take random identities, then what's the fraction of them that what's the fraction of n3 identities sitting inside? And the fraction seems pretty high, right? It seems like if length increases, then this fraction computed numerically, it at least I get that up to about 75%, right? When the length is about 1,200. Okay. So our conjecture is that maybe this thing would either probably won't go to 1, but it should go to some limit r, right? So there is as the length goes to infinity, there should be some this curve would probably plateau out at some r. We really like to know what fraction r that is. Okay, great. Yeah, so there are lots of specific conjectures with lots of pictures in that paper. Yeah, so a lot of them, whenever we talk about words with really long lengths, then we're really looking at basically convex hull of paths paths now, after rescaling, they become kind of Brownian bridge. And then we're looking at like the lower convex hull from Brownian bridges, of which there's a really nice literature that has connections to random partitions and whatnot. All right, so algebraics are interested in finite generation. As a probabilist, I'm very interested in, say, connections with Brownian bridges and Brownian motion. Okay. Yeah, so please let me know if you're interested in this work, and I would love to chat, especially in the polytopes in higher dimensions. Okay, I think that's probably enough. I think I'll stop here. Yeah. Thank you for your time.